We've seen integrals that are improper because you're integrating all the way to infinity, but there are other types of improper integrals. Let me start with an example, or there's another type of improper integrals. Let me start with an example that will illustrate how we have to be careful sometimes when we integrate. So here's a very sort of straightforward looking definite integral, right? Let's integrate the function 1 over x minus 4 quantity squared dx from 0 to 6. And if you just go about this, sort of, just the standard way, we think, okay, x minus 4, that's really x minus 4 to the minus 2. So that's minus x minus 4 to the minus 1, right? That's the antiderivative of the function in the integral. Evaluate from 0 to 6. And so we get, it's really minus 1 over x minus 4 from 0 to 6, which is minus 1 over 6 minus 4 minus 1 over 0 minus 4. Ooh, which is a lot of that's minus a half minus a quarter. Am I doing that right? I think so. It's minus 3/4. Okay, and here's the problem. This is our answer, but this function is always positive, right? We're squaring. So the integral should be positive. Right? But we got a negative answer. That's a problem. That doesn't make sense. And if we graph the function, we see what's going on, right? Let's graph it. Let's graph y equals 1 over x minus 4 quantity squared. And you'll notice pretty quickly, right, if you graph this, that you'll see the issue, right? So we just need it from 0 to 6. Well, think about what happens when you plug in 4. When you plug in 4, you get a vertical asymptote, right? You get a vertical asymptote right here, and the function is actually, go back to the non-dotted line. The function actually looks like this, right? It's sort of your standard 1 over x squared function, just shifted 4 units to the right. But then the area we're looking at is the area from 0 to 6. It's all this area, but we have this vertical asymptote here, and this causes a problem. Right. Basically, you can't ignore this because you can get nonsense answers. In fact, I claim that this integral, so basically the point is this is not okay, what we did up here. Like we really should not have done this up here at the top. It's bad. I claim that this integral actually diverges. The integral from 0 to 6, 1 over x minus 4 quantity squared. Claiming that this, oh my God, my handwriting is so bad. I claim that this actually diverges. And how do you, well, first, okay, so let me explain. So this is improper this integral is improper at x equals 4. right? Because the function is not defined there. And so really we need to break it up into two integrals. This is the integral from 0 to 4 plus the integral from 4 to 6. Right? And so, and let's just focus on the integral from 4 to 6 for a second. So kind of like we did when we integrated to infinity. Infinity is an improper point. It's not really, it's not even on the x-axis. So 4 is an improper point. So really what we want to do is we want to think about integrating just up in the picture. We want to integrate just a little bit to the right of 4. And that's really what we want to integrate. So we want to find this area here, this red that I'm drawing in the picture here. But this is like 4 plus a little bit. Okay, and so actually, and then we want to like let the little bit go to 0. We want to let the limit, we'll take a limit again. So what we're actually going to do is we're going to define this to be the limit as a goes to 4. And I'll say it's 4 from the right. I don't know if you've seen this notation before with this little plus sign up here. But sometimes you want to say if you're approaching 4 from the left, you put a minus sign up here. If you want to say you're approaching 4 from the right, you put a plus sign up here because we are approaching 4 from the right in this picture, right? We would start a little to the right of 4 and move in. So it's the limit of that, the integral from a to 6. And now this is not improper anymore, right? This integral right here is not improper, so we can evaluate it. And in fact, if we do that, so the integral from a to 6 of x minus 4 to the minus 2 power, now we really can do what we did before, from a to 6. And so we can actually write negative 1 over 6 minus 4 minus negative 1 over a minus 4. And now we can see something interesting here, right? Because, okay, this first term is negative 1/2. So we get negative 1/2 plus 1 over a minus 4. And so then this integral up here equals the limit of that expression, the limit as a goes to 4 from the right of negative 1/2 plus 1 over a minus 4, right? I'm just plugging this in for this right here. But now look what happens. If you plug in numbers slightly larger than 4 for a right here, then you get very small positive numbers. So I'm going to say it this way. This is negative 1/2 plus 1 over, a tiny number, tiny positive number. So that's negative 1/2. Really shouldn't be writing equal signs. These aren't, I'm sort of using words, but just think about it this way. This is like, if you're thinking this is negative 1/2 plus 1 over tiny positive, which is negative 1/2 plus, well, 1 over a tiny number is a big number, right? So a big positive number. I sort of like writing things this way because it sort of gives you a sense of what's going on. And so that goes to infinity, right? That goes to plus infinity. So this limit is actually infinite. And thus, the integral from 4 to 6 diverges. And that actually means, that implies the integral from 0 to 6 also diverges, because up here, the integral from 0 to 6 was the sum of two integrals. And regardless of what happens, if one of these is infinite, then the sum has to be infinite also. So this whole integral is infinite. That's kind of the way we interpret this. So that implies that the integral from 0 to 6, really anything that contains the integral from 4 to 6, also diverges. If you do the same kind of computation on the integral from 0 to 4, you will see that it diverges also. So that's why we got the negative answers. We actually got two infinities, and they were canceling out in a strange way, but giving us a nonsense answer. Okay, so this is what happens. We can have integrals that are improper at finite points if there's a vertical asymptote at that point. Okay. I will say that just as before, a good avatar, the functions 1 over x to the p are a good avatar for this again. Except now, instead of integrating to infinity, you actually want to integrate from like 0 to 1, say. Because these are functions that have vertical asymptotes, they all have a vertical asymptote at x equals 0, right? So I'm not looking at the behavior as x goes to infinity. I'm looking at the behavior as x goes to 0. And in fact, you can sort of go through the argument. You can do examples, maybe just to keep the videos reasonably long. I won't go through much examples here, but you can examine the integral from 0 to 1 of 1 over x to the p dx. The 1 doesn't matter. Here it could have been 2 or 3 or 4 or 0.7 or whatever. But it's here where the integral is improper, right? Because you can't do 1 over 0. And so it turns out that this has a very similar answer to in the last video when we did the integral from 1 to infinity. So except it's kind of switched. So here it turns out to converge if p is less than 1. So converges. And then this turns out to diverge if p is greater than or equal to 1. And so I would say check either some examples. Like you could try p equals a half. We kind of did p equals 2 up here, right? Because we were doing a 1 over x squared function. We just shifted it 4 units to the right. And you can give a general argument very similar to the general argument we gave in the other video about the integral except from 1 to infinity. You just have to kind of go through the details. So you could try to write down the general argument also. Try to go through. I would encourage you to do that, but I don't want to make you watch 800 hours of videos. It's better if you try stuff on your own. Okay, I will stop there.